Hello. So today I want to look at properties of vectors and vector operations with a focus on dot and cross product in particular. They have so many nice properties that are associated with the rather strange looking formulas that govern them. And um, this is part of why we like these definitions, is they have lots of really nice properties. So in particular, let me show an example of a really nice property involving dot and cross. Um, let's start with, so for example, I want to prove, let's say prove or disprove. So prove it if you think it's true, disprove it if you think it's not. Prove or disprove that um, v dot w equals w dot v, right? This would be called the commutative law, commutative property for dot product, right? So the commutative property, it means that multiplication left to right is the same as multiplication right to left. So the commutative property for dot product, right? This, I will go ahead and try a few guesses, right? This is a great place to start. If you're wondering, is a property true or not? Try something out, right? So try, how about, let's do V is 2, 1. Let's do W is -1, -1 and 3, right? Let's do that. Let's just try something at random, right? You don't want to try maybe 0, 0 or something super special, right? Because it might mislead you. Maybe something's true for the zero vector that isn't true in general, right? So let's try something sort of arbitrary. I'm picking these kind of out of a hat just to see if the left-hand side and the right-hand side of this identity, do they match or not? So for the left-hand side, I'd have 2, 1 dot -1, 3. So I get 2 times -1 plus 1 times 3. -2 plus 3, -1. Okay. And then right-hand side, what would that be? W, I have -1, 3. And then I dot that with 2, 1, which is going to become what? It's going to become -1 times 2 plus 3 times 1 is going to be -2 plus 3 is going to be -1. Oh, they match. Good. Okay. So these match. And so I'm feeling pretty good about this identity. I tried something at random and it worked, right? Now I feel like this is more than a coincidence though, right? Look at what happened. Well, 2 times -1 was the same as 1 times -2. And 1 times 3 is the same as 3 times 1. Oh, there we go. Well, they had to be the same, right? Because when you do your dot product, whether I did 1 times 3 or 3 times 1, and then same thing for the x coordinates, it didn't matter. It wasn't going to affect the value. So I'm pretty sure this is true, right? By working out an example, I'm feeling good about this property, right? And um, if you don't if you feel unconvinced after one example, maybe try 2 examples, try 3 examples, do a couple until you feel like you believe that it's true, right? Um, a lot of times in problem solving, um, they call this get your hands dirty, right? This is very clean, this is very abstract, right? So get down and play with actual examples, dig around in the dirt a little bit, right? Get your hands dirty with really concrete, specific examples to get some intuition for what's going on, right? So I'm going to try to prove because our example worked out, and I see some structural reason why this might generalize. So let's try this. So here's how I could prove this. So first, let's start with a nice statement of what it is exactly that we're trying to prove. So this theorem, and this theorem has a special name, commutative property of dot product, right? Commutative property of dot product is the name of the theorem that we're trying to prove. And not every theorem has a nice name. It doesn't have to have a special name every single time. It just be something that's true. But this one has a special name, commutative property of dot product. So what is this theorem? Well, n is going to be the dimension. And then we're going to have 2 vectors of a dimension n, right? So pick some natural number to be the dimension and pick two vectors of that given dimension. What's the conclusion? The conclusion is going to be that v dot w equals w dot v. Right? That multiplication given by dot product is commutative. So that's first thing you do is when you're writing a proof is state very clearly what it is exactly that you're trying to prove. Now I'm going to write out the proof of what we're trying to prove. And what I'm going to write out is this. I'm going to say, okay, let as given, right? So we let n be a natural number, and just sort of declaring the variables as they were declared in the proof statement. And then I'm going to give coordinates to v and to w. And I'm going to say where those coordinates live. These are all real numbers, right? That's what we have for the coordinates of vectors. Right, so this is the start of the proof is just declaring all your variable, right? Set up all the symbols and say exactly what all the symbols mean. What set do they come from? Are they natural numbers? Yeah, n is, right? Are they real numbers? Yeah, the components of v and w are. V and w themselves are n-dimensional vectors, right? I've declared every single symbol that I'm going to use. This is a very standard and very essential part of proof writing is declaring all your symbols. There we go. Then what do I have next? I have I'm going to prove that these two dot products are equal, right? So let's now calculate the dot products, right? And I'm going to calculate v cross w, and I'm going to do it in what's called transitive chain notation, right? So I'm going to say what v cross w, sorry, v dot w, not cross, v dot w is, and I'm going to write one quantity, which equals another quantity, which equals another quantity, which equals another quantity, which equals another quantity, until I hopefully reach w dot v, until I reach the goal, the other side of the identity, right? That's how I'm going to structure this. It's called a transitive chain. A very nice way to structure an argument like this. So what do I have? First, I do this dot product, v1, w1, v2, w2, plus dot dot dot, plus vn, wn, right? Then, just like in my example, right? What made these equal? Well, the fact that 3 times 1 is 1 times 3, 2 times minus 1 is minus 1 times 2. Same thing here. Just generalize the example. Switch those products. v1, w1, make it w1, v1, and so on for all the other coordinates. This is commutativity of ordinary real number arithmetic, right? Now, what happens next? Now you can put it back together, right, as a dot product going the other way. Right, what I have written there, w1, v1 plus w2, v2, and so on, out to wn, vn, that's exactly the dot product of w with v. So we're done. As desired. And you can put a nice little element of proof symbol, little Halmos box, right? So there's our proof. Now we're done. So this is a proof of commutativity of dot product, of the commutative law for dot product, right? Very, very concise proof, very formal. Everything works out nice and clean, right? So this means anytime you want to trade the order of a dot product, you can, right? Let's look at another example. Let's say prove or disprove commutativity of cross product, right? So commutativity of cross product, let's look at that. So this would be v cross w equals w cross v, right? Okay, so let's look at, let's try, again, let's get our hands dirty, right? That should be your first step, is try a few examples, right? So get your hands dirty, right? This is anytime you're dealing with something abstract, try it out in a couple of very concrete cases. That's how you build an intuition for the abstract, is by noodling around in some concrete cases. So let's start by getting our hands dirty. Let's try, let's see. Let's try, how about v equals 1 minus 1, 2. And let's try w. Let's see if this, and let's say in R3. Let's say here everything is R3, just for, it's kind of the standard place where cross product is defined, for at least in the context of Calc 3. So let's do v as that. Let's say w is, let's say, how about minus 2. Let's say minus 2, 2, and minus 4, right? Let's say this is our v and w. Okay, well, let's try the left-hand side, let's try the right-hand side, and let's see if they're equal to each other. So left-hand side, what do I have? I have 1, minus 1, 2, cross, minus 2, 2, minus 4. Okay, so now I do the cross product, and what do I get? Well, I have my, I start with this one, right? What is that going to be? 4 minus 4, right? Then I am going to have this one is going to be what? It's going to be negative 4 minus negative 4. Then I'm going to have this one is going to be 2 minus 2. Wow. All right. So I actually get 0, 0, 0 for that left-hand side, for v cross w. So then, and when I say left-hand side, I'm referring to this left-hand side, the left-hand side of the proposed identity. So there's the left-hand side, right, in my example. All right, now let's try the right-hand side. So right-hand side, what do I have? I have now w cross v, minus 2, 2, minus 4. Okay, so what is this? This is now going to be, let's see, I'm going to start here in the x-coordinate, so I get 4 minus 4. Then I go here for the y, is going to be minus 4 minus 4 is plus 4, right? Then I'm going to go here for the z, it's going to be 4 minus, 2 minus 2. And I get 0, 0, 0. Okay, they match, right? Okay. But I'm not going to try to prove this yet. Yeah, they matched, but it seemed like something kind of weird, like collapsed here. I got 0. I just got the 0 vector for both of my answers. So yeah, 0 vector equals 0 vector, but it doesn't seem like a general case. It seemed like something sort of special happened here. I'm not convinced that this is true in general, just because it was true in this case where they were both 0. So here I tried one example, right? This is sort of example 1. But, something weird happened here. I just have a bad feeling about the fact. It doesn't feel like it was a really general case, right? That represents what could happen, right? Let's try another example. I'm going to try, let me try the same V, but I'm going to pick a new W. I'm going to pick, how about, let's see, how about something simple? Let's pick, I don't know, 0, 0, 1. Let me pick that, right? I'm going to pick a very different W. You may as well pick some zeros, right? Make it easy to compute with, but just something I didn't like. I got a bad feeling about the last one, right? The fact that they both came out to zeros. Let's try this. So let's try this left-hand side now. V cross W, right? So what does this give us? Now, if I do the x component, right, I get 1, right? Because it's, minus 1. Yeah, minus 1, minus 0, right? Here, let me write this out. Minus 1, minus 0. The y component, I do this minus this. So I get 0, minus 1. And then the z component, I'm going to do this and this. I get 0. Okay. So this is -1, -1, 0. Now let's do the right-hand side, W cross V. So here, what happens? Now I'm going to have all the X, the Y, and the Z. And what does this become? This becomes 1, 1, and 0. Ah ha ha ha. These do not match, right? There we go. So that first case, something weird did happen in that first case, right? The fact that it just got 0 vectors, there was something special going on there, right? So sometimes you want to try a couple examples to convince yourself that it's, before you're convinced that it's true, and you go do all that work of trying to prove it, right? Um, Here, they did not match. So what do we have here? We have a counterexample. A counterexample for an identity like this is a perfectly good disproof. You don't have to do anything more. You don't need to write out a generic argument like this to show that a proposed identity is not true. You only have to find one example for which it's not true. And that's what we just did, right? So we just found an example, a counterexample, that we have a very concrete counterexample, right? Thus, V cross W equals W cross V is not true. It's not true for all V and W in R3, right? It's not an identity, right? It is not an identity. Or another way to say it in this case is that you could say that cross product is not commutative, right? That's a perfectly good way to say what we learned here. So a cross product is not a commutative binary operation, like dot product was, right? Dot product is a commutative binary operation. You can change the inputs and you get the same result. Cross is not a commutative operation. So there we go. So there's an example of proving something true here for dot products, right? Proving that dot products are commutative, and disproving something false, right? A proposed, identity that would turn out to not be an identity, right? That cross product is not commutative. So there's an example of a proof of an identity and a disproof of an identity, right? So this is if you're in my course, right, you'll notice this is always one of my favorite types of questions to ask. I always put these on homeworks. I always put these on exams. Prove or disprove, blah, and then I write out some identity. If it's true, you prove it. If it's false, find a counterexample, right? And what you see here is exactly the workflow that you want to do. You want to you try some examples, and if they work out and they seem generic, then maybe try to write a proof. If you try some examples and one of them leads to a counterexample, then you're done. Then you just say, hey, there it is. There's my counterexample. The identity was not true. Right? So there we go. There's the commutative property for dot and commutative property being proven, and the commutative property for cross being disproven. Right? All right, so there is an identity each for dot and cross, and we will call it good for the moment. These are kind of simple identities for properties for dot and cross. There are way more complicated ones that don't work kind of just with this little, let's do a transitive chain and do the calculation to prove it kind of properties. Ones where you need a lot of geometry or trig or a diagram, associated diagram. So we'll look at those next. They're more complicated. So, all right. Thank you.